All right, section 4.5, we're going to get into a little more specialized triangles now. We're going to have isosceles and equilateral triangles. So these are specific cases that don't work if the triangles aren't isosceles or equilateral. Okay? And there's a lot of definitions and a lot of theorems to this. So first thing, with an isosceles triangle, you kind of need to be aware of all the vocabulary that goes with it. First, you have, since it's isosceles, it has two congruent legs. We call them legs. The two angles that are congruent are called base angles because in order for this to happen, you have to have two congruent legs, two congruent base angles, and there's theorems for that. The I won't call it the bottom side of the triangle because it doesn't have to be the bottom, but the side of the triangle that's not congruent to anything is called the base. And then the angle that's not congruent to the other two angles is called the vertex angle. All right, first theorem, the isosceles triangle theorem. That's what we'll call it. We will not call it theorem 4.3. Okay? If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So in this triangle here, I know the two sides are congruent, so it's isosceles. So that means that this angle is congruent to this angle. Okay? If sides are congruent, then the angles are congruent. Because there is a converse to this, that if two angles are congruent, then the sides opposite those angles are congruent. So this one says if angles are congruent, then sides are congruent. And then there's one more theorem. The bisector of the vertex angle, so the odd angle out, if there's this line right here that bisects that vertex angle, makes two congruent angles up there, then it's also the perpendicular bisector of the base. So it means it splits it in half and it's perpendicular. Okay, that's kind of a useful theorem in problems. We can do numbers with this. All right, we're not going to prove that theorem today, so we'll just skip this one today. If you'd like to do it, then I can look it over for you if you'd like. All right, so let's look at this. I give you this triangle. It's got some marks on it. Those are important marks. I want to know why these two statements are true. So on the first one it says angle WVS is congruent to angle S. So why is this angle congruent to this angle? And if we look in this little triangle right here, it already had sides congruent, so that makes the angles congruent. This is by the isosceles triangle theorem. And that is how you abbreviate isosceles triangle theorem. Alright, and then I'll switch colors. We have TR, which is this whole side, congruent to this whole side. And looking at the markings we have, you have angle R is congruent to angle S. So if the angles are congruent, then these sides have to be congruent. That is by the converse of isosceles triangle theorem. Okay, that's how those theorems work. Alright, we want to find the value of angle Y. This would be that bisector theorem, because we have an isosceles triangle, because the two legs are congruent. They have an angle up at the top, bisected by this, so that means this is a right angle and these are equal by the theorem, by theorem 4.5. So that means there's a right angle on this side as well. So if this is 63 and that's 90, then this one has to be 27 in order for the triangle to add up to 180, which means since these two are equal, Y has to be 27 also. Alright, we have a new thing called corollaries. These are like little side notes, you know, like when we used to write letters to people and we would put a PS at the bottom. That's what a corollary is. Here's the theorem and then it has a PS after it. That's a corollary. Okay? So all of these will say corollary to theorem whatever. Okay? Theorem 4.3, this is the isosceles triangle theorem. So this would be a specific case of this isosceles triangle theorem. It says if a triangle is equilateral, then the triangle is equiangular. And then the second one would be a corollary to the converse of the isosceles triangle theorem. this one says if a triangle is equiangular, then the triangle is equilateral. Okay, these are useful only when equilateral triangles are involved, but they're there. Alright, so a little challenge problem for today. A square and a regular hexagon are placed so that they have a common side. Find the following. I want the measure of angle SHA and the measure of angle HAS. So I want the measure of this angle and the measure of this angle. So let's start in. What do you know about a square? A square has to have 4 equal sides, right? Which means if the square and the hexagon have a common side, that means all the sides of the hexagon also have the same sides. So that makes this little triangle I formed out here an isosceles triangle. Okay, so that's round 1. Round 2, the squares have 90-degree angles here, right? A hexagon has to add up to the 6 minus 2 times 180. Remember that formula? So if you take 4 times 180, you get 720. So a hexagon has to add up to 720. Since all the sides are the same, all the angles have to be the same as well. And so if you divide that by the number of sides, you get that the hexagon has a 120. Okay, right here at H, all 3 of these angles have to add up to 360. So if we take 360 minus 90 and then minus 120, we have 150 left. So that's SHA, 150. Alright, then we have this isosceles triangle. We know that if it's isosceles, the angle here and here have to be the same. We also know it has to add up to 180, and we already know that the vertex angle is 150. So if we take 180 minus 150 and then split it in half so that both angles are the same, we get 15 degrees. Okay, because the 2 of them together have to make 30, so one of them, they each have to be 15. Alright, another word problem, because this is what this is good for. 5 fences meet at a point to form angles with measures x, 2x, 3x, 4x, and 5x around the point. So picture we're in a horse lot, and you've got 5 fences that all come in and meet at one point. Angle measures x, 2x, 3x, 4x, and 5x. Obviously not drawn to scale because the 5x angle should be way bigger than the x. What do all 3 of these have to add up to? So if we add all 5 angles together, they should add up to 360 because they make a full circle here, right? Okay, so if we combine like terms, so we do 1, because this is 1, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and we solve that, so we take 360 divided by 15, we get 24. Alright, and they want the measure of each angle, so we're going to plug that x back in. So this one is 24 degrees, this one is 48 degrees, this one is 72, and then this one is 96, and then this one is 120, all the way around. Okay, so this section doesn't necessarily have to be all proofs. There's some problems that can be part of it as well.